Another strength criterion that is widely used for materials that exhibit different strength in tension and compression is the so-called Mohr-Coulomb criterion. This criterion is particularly useful in geotechnics for materials such as clay in drained conditions, that is when water has been removed. But it can also be applied to building materials such as concrete, brick or mortar with some approximations. The theoretical origin of this criterion is related to the concept of friction in physics. Consider a block resting on a rough plane which is acted upon by a compression force N normal to the plane and a force T parallel to the plane. It is well known that the block will not slide if the modulus of T is less than or equal to N times the tangent of phi, where phi is called angle of friction. This condition is often rewritten as modulus of T less than or equal to N times mu, where mu is the tangent of the angle of friction and is called the friction coefficient. Both phi and mu depend on the roughness of the surfaces in contact. Note that according to this criterion, if the block is not compressed, any infinitesimal horizontal force will cause sliding of the block. This is the so-called Coulomb criterion for the stability of the block. Coulomb was a French scientist who lived at the end of the 18th century and was an engineer in the Royal French Army. In the 19th century, Mohr reformulated Coulomb's criterion in terms of normal stress sigma and shear stress tau acting on an infinitesimal surface passing through a given point in a three-dimensional body. Namely, Mohr-Coulomb's criterion states that the modulus of tau must be less than or equal to minus sigma times the tangent of phi plus tau 0, where phi is now called angle of internal friction and tau 0 is the simple shear strength or cohesion of the material. If we compare this expression with Coulomb's criterion, we will note a minus sign coming from the fact that compressive stresses are negative and a non-zero cohesion which was added because most materials can withstand the shear stresses even if no compressive stress is applied. Sand and gravel are examples of cohesionless materials with tau 0 equal to 0. The critical index underlying this criterion is thus a combination of normal and shear stresses. In the sigma tau plane or Morse plane, this criterion is represented by a domain bounded by two half-lines departing from a common origin and symmetrical with respect to the sigma axis. If the largest Morse circle corresponding to a given stress is entirely contained in this domain, the stress is deemed to be permissible. And here is an example of permissible stress. Well, now we want to express this criterion in terms of principal stresses. Let's refer to the last picture and prescribe that the radius of the largest Morse circle is smaller than or equal to the distance between the center of the circle and the boundary of the domain. Thus, 1/2 of sigma max minus sigma min must be less than or equal to tau 0 cotangent of phi minus 1/2 of sigma max plus sigma min times the sinus of phi. That is, 1/2 of sigma max minus sigma min plus 1/2 of sigma max plus sigma min times the sinus of phi must be less than or equal to tau 0 cosinus of phi. Let us rewrite this criterion in terms of allowable tensile and compressive stresses sigma t and sigma c. We must express cohesion and friction angle in terms of these stresses. To do this, let us draw the Morse circles that correspond to simple tension or simple compression and are tangent to the boundary of the domain. we find that 1/2 of sigma c times 1 minus the sinus of phi is equal to tau 0 times the cosinus of phi, and similarly that 1/2 of sigma t times 1 plus the sinus of phi is equal to tau 0 times the cosinus of phi. If we solve for phi and tau 0, we get that the sinus of phi is equal to sigma c minus sigma t divided by sigma c plus sigma t, and that tau 0 is equal to 1/2 of the square root of sigma c times sigma t. Then it is quite easy to show that Mohr-Coulomb's criterion can be rewritten as sigma max divided by sigma t minus sigma min divided by sigma c less than or equal to 1. As either one of the three principal stresses, sigma 1, sigma 2, and sigma 3, can be the minimum or the maximum normal stress, this inequality corresponds to 6 inequalities in terms of principal stresses. And these inequalities define a domain in the shape of a pyramid in the space of the principal stresses. The vertex of the pyramid is on the so-called hydrostatic axis, defined by sigma 1 equal to sigma 2 equal to sigma 3, and the domain is open on the side of the negative hydrostatic stresses. If one of the principal stresses is 0, for instance, if sigma 3 is 0, the material is in a state of plane stress. In this case, the 6 inequalities that define Mohr-Coulomb's criterion are sigma 1 divided by sigma t minus sigma 2 divided by sigma c less than or equal to 1, sigma 2 divided by sigma t minus sigma 1 divided by sigma c less than or equal to 1, sigma 1 must be between minus sigma c and sigma t, and similarly sigma 2 must be between minus sigma c and sigma t. These inequalities define a domain in the shape of an irregular hexagon in the plane of the two principal stresses sigma 1 and sigma 2. We can note that unlike Galileo-Rankine criterion, Mohr-Coulomb criterion accounts for the decrease in strength of the material when subjected to combined tension and compression with respect to simple tension or compression. And this decrease is experimentally observed in materials such as concrete.